see. So, first of all, I have here the tests finally. Well, at the break, we can just, I'm going to let you take a look at them, or yes, take them away actually. Here we go. So, no, man, wait a minute. I'm forgetting what I'm doing here. All right, so to begin with, I thought I'd just take a quick look at a project-related issue. So, but first, I'm sorry, questions, opening questions, administrative difficulties. All right, so this is, I just thought I'd accumulate in one place a couple of the, make sure that you understand the issues regarding scoping, which is perhaps the rather complicated part of all this. What you see here is a contrived little program that illustrates some of the problems that you will face. I've talked to a few groups about this, and so I thought I'd just say it generally. So, in this particular example, we see a number of things going on that are of some interest. First of all, you notice that we refer to this variable x2 here, which is it's actually a local variable inside f2. And why do we know that? Well, because there's this assignment down here. Now, you might have thought, oh, no, this is bad. You can't assign to something, you can't use something before it's assigned to. Well, you aren't necessarily using something before it's assigned to here, because as you can see, there's a while loop, and x2 might, depending on how b works, x2 might very well get set before it's used. So the compiler can't complain about this particularly. It would complain in Java, by the way, because it would say, I'm not absolutely sure that x2 is set, but here it can't. But now the interesting thing is that x2, even though x2 is defined outside f2, and even though x2 is made a local variable after the use of x2 here in this print statement, nevertheless, this print is supposed to print this value of x2 down here, the lower value of x2. So you might consider the question of, well, what exactly does this mean? What is the implication? And in fact, and as for x1, well, it prints the x1 that's defined out here after the definition of f2. So it prints an x1 that's right out here. It could also, the definition of x1 could have occurred even after this class definition. So what that tells you is that you can't start linking identifiers to declarations until after well, basically what it tells you is you've got to take several passes through this program. So, for example, before you can look at this, can figure out what this x1 and x2 mean, you first have to have scanned f2 to see whether it contains assignments to it. You have to have scanned f1 to see whether it has contained assignments to it. In fact, you have to have scanned the entire outer level of the program in order to see whether it has an assignment to x1. And to see which assignments they are. So first you have to find declarations, then you resolve. So that's one thing. And the order in which you do this is rather interesting because, of course, once you get into this, you'll see that it involves basically a rather complicated recursion, in which the first thing you do is you look for all of the assignments sort of at the outer level, that is not inside any def or class. You look at all the assignments to variables. Then you go back and you resolve these, but in the process of doing that, you will encounter function definitions like F2, at which point you're going to have to repeat that entire process in miniature inside F2. That is, you have to scan the body of F2 for declarations and then go back and resolve. So it's a recursion within a recursion that you're doing here. It becomes rather interesting, to put it mildly. One little glitch or feature of Python that I think some may have been unfamiliar with is illustrated right here. Print A1. This is an error. Yes, A1 is defined. It's defined right up here inside the class A. But the rules of Python, but you see this statement here is inside the definition of where it's supposed to be, it doesn't seem to be indented correctly. Tut, 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 tut. These two things, x1 equals 12 and print A1, are supposed to be indented inside F2. So this printing of A1 here is an error because the scope of these, because in a class, the scope of the declaration, the class member declarations, A1, F, and so forth, does not include the bodies of any of its member functions. So just plain A1 here is invisible. A1 is visible out here. You can say A2 equals A1 plus 5, for example, but not inside. The only way you can get at A1 and A1 is to say self.A1, in other words, to reference an object of type A, class A. So there's this funny little hole in the scope that you have to deal with. Now, all of this can be done. All of this is perfectly reasonable to do if you have the right abstractions to help you. And basically, we talked about that in lecture. I said at that point that, well, what we've got here are CS61A environment diagrams, except the only difference being that since we're not actually executing the program, instead of having values you have linked to identifiers, you have other information linked to the identifiers, information that the compiler knows linked to the identifiers. So anyway, this is a charming little exercise in recursion and trees. If there's one thing, if you didn't learn about trees in CS61B, you will now, right? And 61A, then you definitely will now, because you're going to be climbing all over these things like a tribe of monkeys, getting all this to work. So it should be fun. Right. Okay, so that's basically the word I've been giving to various groups who've come to me asking about this. I suppose I should have waited for the rest of you to come and ask me about this, but somehow I didn't think there was enough time in the day, so I thought I'd just say it in lecture. Okay. All right? See that? Good. Okay, well then let's get to the main topic of the afternoon, or the morning, I should say, which is runtime organization. This is an entirely new topic. We have so far done parsing, lexical analysis, and parsing. We've done static analysis, which when you're done is going to produce this decorated tree. So you have an abstract syntax tree, and you'll have these little attachments to the identifiers that let you know what each kind of node, what each identifier refers to. And at this point, you can assume that all the remaining static errors are gone, and now it's a matter of doing the rest. So the rest of the compiler has to do with what we call the dynamic semantics. In other words, basically what happens at execution time. So you're generating runtime, you're generating code. The purpose of the code is to do the execution. Or if you are producing, you might also be producing say, another version of the AST so that it can be interpreted. In any case, it involves execution. And also, in the classical compiler, where you're actually producing machine code at the end, well, actually, this applies to any compilers. There is classically a separation between code generation and what we call optimization, which is basically, it means improvement, not optimization. Optimization would be making it perfect, but we can't do that, so we just try to make it better. That's an interesting topic. It's acquired somewhat of a new, well, it's become more interesting of late because people are interested in a very difficult problem of optimizing multi-processing programs that involve that run on multi-core computers or distributed computers or something like this. And if you had, to the extent that you have language support for that versus library support, it can result in some rather interesting problems that we might have time to get into. All right, but first, when dealing with any problem, it's best to understand exactly what the target is, what you're trying to accomplish. So the term virtual machine you've probably encountered before now. It's not quite the same as virtual memory, but the virtual part is similar. The idea is that rather than target, it is convenient to target a somewhat idealized or cleaner version of your hardware than is actually presented by the hardware. This is especially true in the case of certain architectures, such as, for example, the IA32, otherwise known as the 8086, otherwise known as everything Intel produces, that has basically accreted architecture or accreted features over the years. So they've unfortunately had to face the great bugbear of backward compatibility, and so they incorporate these instructions that come to us from the early 1980s or before, and were originally intended to run on an 8-bit data path 8088 computer that started this whole line. So it's somewhat of a problem. It's a kind of a messy architecture, and it's nice to be able to, and so what you'd prefer to do is to abstract away from it. And this is hence the term virtual machine. Now, some of these can be, you can't, I mean, technically, virtual machine is like this reflexive relation. So a machine architecture all by itself, a bare machine architecture, could be called a virtual machine, and we could target all of our compilers for the 8086 and then have a back end that somehow converts that into your actual hardware, but that's not very convenient. In the case of Java, there's a very elaborate relatively elaborate virtual machine that has a lot of, unlike ordinary hardware, it has a lot of information about types. So in Java, the virtual machine actually understands things like object-oriented programming and methods and all that sort of business. And the virtual machine actually does type checking. There's type checking in the virtual machine in the case of Java, so that not only Java compilers but also other compilers can target that machine. And we're going to be a little bit classical here because it's fun actually. So what we'll do is just a nice, pretty straightforward thing where we have an abstraction of the hardware, and then we'll have and then as for the runtime system that we actually run it on, what we have are a set of conventions for using that hardware that together are called the application programmer interface, or Sometimes it's basically what the programmer has to deal with. So if you look in a manual for example, there's online we have manuals for the IA32, and somewhere in there they have a section on the programmer's interface that talks about things like calling conventions that aren't built into the hardware, but they're just what everyone does when you're using the IA32. So what we're trying to do here, several things. One thing that's important is that we can view the decorated AST that comes out of semantic analysis as itself a kind of program. It's a form of the program, and it has certain presumably well-defined semantics. I mean, what this program is supposed to mean. And if we convert into machine language, one of the things we have to do is to preserve that meaning. So when we translate it, it's not as if the meaning suddenly materializes when we translate it, and it can be anything, and it's an empirical thing. Whatever we happen to code, that's it. No. There is a standard, which is we have an intended meaning for the AST, and the machine code has got to do that. But that said, there's a lot that's usually left unspecified in these semantics. For example, in C, it's unspecified what order you evaluate parameters. And this actually makes a difference. On exactly 2 occasions in my entire career, I've actually run into cases where this makes a difference. One of them was just within the last year, as a matter of fact. I was overjoyed. I took a coffee break and celebrated when I found it because it's so rare. But it does happen. So that's not specified. In fact, C is notorious for not specifying things. It doesn't say what happens if you overflow an int. It tells you what happens if you overflow an unsigned int, but it doesn't say anything about overflowing an int. It doesn't tell you what happens if you access the element. It doesn't tell you what happens if you access the element beyond the last element of an array, or if you try to two beyond the last element of the array, and it doesn't tell you about what happens if you access the element before an array. These are unspecified. It doesn't tell you what shift does when you give it a negative value. It doesn't tell you what mod does when you give it negative values. They were trying to do was to accommodate, and of course it doesn't tell you what the ranges of any of the types are, except it does give minimal ranges. They were trying to accommodate all kinds of different hardware. In retrospect, I would have taken a different approach. I would have said, I'm going to do the one that's right, and if that means that it's slow on some particular piece of hardware, well, that's the hardware's fault. Right? So, but politically they couldn't do that. So we're left with a largely unspecified language. So that means that you, the language designer, can choose what to do, and the compiler can choose. The compiler writer, the language implementer, can choose what these do, and you have to fill in all of these semantics. Now, we also want the execution of our programs to be as fast as possible, as fast as feasible, I should say. But of course, this is and sometimes that's not just desirable; it's absolutely necessary. As in the case of real-time systems, the thing about real-time systems is that you want things to be predictable more than anything else. You'd also like the program not to be too much bigger than it has to be. Of course, I'm sure you realize that these last considerations sort of diminish in importance as time goes on, at least for a fixed application, because memories have been getting bigger. I mean, we do things these days, we routinely do things in our programs these days that would horrify a programmer from 30 years ago. Would have horrified my younger self. We use up profligate amounts of memory. It's just terrible. And I mean, you can't swing a cat in less than a megabyte these days, and it used to be that we ran on machines that had less than 64 kilobytes. So, I mean, you see that things have changed considerably. Nevertheless, getting too big can be a problem, and the smaller the better in general, as long as you don't have to spend too much time on it. So, of course, these goals conflict with each other And they also conflict with the next goal, which is that you'd like these things to compile quickly. You'd like the compiler to be fast. Now, there was a time when old-timers would argue that, no, you don't. That breeds bad habits. It's like the argument about whether you should tell kids about condoms because that will cause them to have sex or something like that. It's giving people fast compilation. There was a school of thought that this is bad, and that you should force people to think before they submit their program to be compiled. Well, I think attitudes have changed since then, especially if you're the one sitting at the terminal waiting for your program to compile. So these are conflicting goals. So why would speed and size be conflicting goals? Why? I mean, if you have a smaller program, doesn't that mean there are fewer instructions? So doesn't that mean that it should execute faster? What could go wrong? 1, 2, yeah? What do you think? And inline functions, meaning expand the code, just substitute the body of the function for the call, and of course this increases size, but may increase speed. Right? Yeah. Right. Yeah, memorization. I don't know that. Don't know many compilers that do memorization, but certainly loop unrolling. Loop unrolling refers to taking a loop a for loop whose bounds are known. For example, it's a loop 1 to 3, and simply getting rid of all the setting and testing of code and just replicate the body of the loop 3 times. This is particularly useful in scientific applications because when you do that, you often make it possible for later parts of the compiler, the optimizer parts, to really go to town and speed things up. Okay, so the problem, as a result, these compilers can get kind of complicated, and you get all these interesting little bugs that creep in because of these funny combinations of you're trying to make the code faster. The architecture you're trying to make it faster on is kind of irregular, and therefore your program becomes irregular, and things become rapidly very interesting. Oddly enough, my own experience with the GCC compiler is that most of the bugs seem to show up at low optimization levels because they've concentrated so much on the optimizer that they've ignored what happens when you don't optimize. It's kind of a funny thing. Okay, so there you go. It's sort of the background of what we're doing. Now, the sort of theme that we see in classical code generation is that we want to make the data structures, from the point of view of the compiler, we want to make the data structure of the data static. You want things to be known at compilation time as much as possible. So, for example, the implementation you see described for Python objects is that they have some sort of a dictionary in them. And finding and assigning to a member of this object is a dictionary lookup process. Well, you really don't want to have to do that unless you really have to. In Python, in pure Python, things are so dynamic that you're forced into something like that. This is also the case with some other scripting languages. In the case of Java, however, the language is designed in such a way, the restrictions on the language are such, that after compilation, you know where every field of an object is going to be, and you know what fields are there. And this is a desirable thing. You are able. That means because that means that the code that you have to produce fits the hardware very nicely. Hardware doesn't tend to have things like look up in a dictionary for where this field is and then set that. It doesn't, even if it did have that instruction, it would be a slow instruction, so it tends not to do that. So, and the other thing is that falls into this, become increasingly complicated these days, is the treatment of the memory hierarchy. So, on the typical machine, people call it the von Neumann architecture, but it's just the way these things work. You have fast memory and progressively slower memory. It used to be you had registers and main memory, period. That was it. Well, if you didn't include the disk, which was a separate category. So registers and main memory. Now you have registers, you have cache, several levels of cache, and then you have main memory. And sometimes you have local memory and global memory. It becomes pretty messy after a while and rather difficult to deal with. But in general, you'd like to keep operations that can be done locally. The more locally, the better, if that actually works. So now, when you're trying to do compilation, there are several things you want. First of all, you'd like to avoid as much as possible things that affect that use the entire program to do an optimization. You have to do this to do a good job. In some cases, you have to do it, but you would prefer to avoid it because typically, especially optimizations, are not linear time. They're super linear time, which means that as the size of the program grows, the compilation time might decrease and or scale badly. So what you'd like to do is, if you're going to do a complex optimization like that, you'd like to keep it as contained as possible. You'd like there to be a sort of typically a maximum size for the amount of code that you have to analyze at any given time. That is, we keep things as local as possible. And we basically we'll do a few things. We'll make some simplifying assumptions, conservative simplifying assumptions about what the code we use does. I mean, you can do some very bizarre things in machine language. We'll sort of discipline ourselves not to do that, to simplify our analyses. Okay. So let's see. Now we're going to start talking about actual semantics. So I think this is a reasonable time, having said some initial boilerplate blather. I think it's reasonable to pause at this time. The tests are up here. Now this is a sheet with last names and test numbers on it. So all the tests have a little number in the upper right-hand column. So you can find out where your test is. Please try to keep these in order. I know that's going to be hard, but please try not to mess up the deck. So let's take a break, and you can grab your tests if you like. In fact, let's just divide this into two piles. So
and they're in order by number?
They're in order by number. So these are the top numbers.
Are you going to post new notes for this, for runtime and all that? Because the notes ended now.
I don't, there might be a few. I don't think it'll be necessary in general. We'll see. Because the lecture notes are pretty, say most of what I want to say.
No, I just ate breakfast. It's fine.
Are we supposed to put them back after?
Number 11.
No, you can keep them. dangerous. So if you have any questions or disputes about the grading, see the TAs. There's one now. Uh-oh. Somebody took your test? Pardon me?
That'll show up probably.
Oh.
But yeah.
All right, well. Does someone have test number 58? Somebody take an extra test? Is that yours? That's yours. Oops. Okay. What's your test number?
Make sure that I didn't read that incorrectly. Oh, I read the one right next to mine.
Oh.
Sorry about that.
Okay, let's get started again. All right, let's get into some actual material here. So during the semantic analysis stuff, we talked about scope, the scope of a declaration, the section of text, either at runtime or at compile time, that to which a certain declaration applies. Now there's a parallel concept, a related concept, during execution, which I'll call lifetime. It's sometimes been called extent, but I'll call it lifetime because that's sort of more, I think, evocative, I suppose. So that refers to the period of time during which a particular object, a particular thing exists, be it a variable or an object. And it's, so variables have lifetimes. We also have the lifetime of a procedure frame or activation. So you call a procedure, all of the execution time information that's associated with the execution of that particular call of the procedure is called an activation, and it has a particular lifetime too. That usually until the procedure returns. Although, for example, although you know that from your experience in 61A that things get a little bit complicated when you have things that return procedures as their arguments, or as their values. Now this concept, again, lifetime, is dynamic. It is not something the compiler deals with, the semantic analyzer deals with explicitly, because in general because it's something that happens during execution. So the code that's generated controls what the lifetime of these things is. Now, so in an ordinary program, in most programming languages, you're familiar with the fact that these procedures, the procedure activations, nest inside each other. So I call P calls another procedure, and before P returns, before that call on P returns, that other procedure will have returned. P defines some local variables, and the procedures it calls define local variables. Before P returns, it will have all of its local variables will have disappeared, and all of those of the procedures it calls will have disappeared. So this is a nested structure, and it's strongly suggestive of the classical stack implementation that is actually used to hold all of these things. Now, on the other hand, you have a bunch of other variables, such as variables that are declared outside of functions, global variables, or file scope variables, as they're called in C. And you have variables that have been allocated by means of new. So these are dynamically allocated variables. And their lifetimes are not anywhere near as neat as that. So as again, this leads to some sort of memory layout, the classical memory layout. This is the classical Unix memory layout, I guess, although other things use it, in which you have instructions, you have the static data, which is these global variables, things like that. You have an execution stack that's growing downward, and you have a heap that's growing upward. I presume that this is review from CS61C. You've seen something like this, but it's useful to take another look. Now, there are many variations on this. There's no particular reason why the execution stack has to grow downward. It could also grow upward. There is no particular reason. There are also architectures in which the instructions do not start at the beginning of memory. They start somewhere in the middle, and they grow downward as you add more modules. And of course, the heap could go anywhere as well. So this is just an example. This particular layout is useful because these two sections here, the instructions and static data, for a standard program that gets loaded once and then executed and doesn't do any dynamic loading, these two things are naturally of a fixed size, and then these two things both want to grow. So you sort of want an open end at one end of them, and it's convenient to have them just on opposite ends of virtual memory. So this is, by the way, a place where virtual memory sort of comes into its own because because it's convenient to assign this a very high address, even though if there was actually that much memory, you'd be paying considerably more for your machine, especially on the new 64-bit machines. Oh yes, that's great. Okay, so what I referred to as an activation record is basically all of the information that's required in order to execute a procedure. So we call that an activation record or a stack frame, are typical terms for this. Now, again, classically, one does put these things on the stack. There's no particular reason why you have to, aside from the fact that that's often the fastest thing to do. But, for example, you can also you can put them on the heap, and there are implementations that implement various exotic things such as continuations and threads and so forth, where that's basically what you do. In fact, with a thread, you have to allocate space for the stack itself on the heap, in effect. We have typically a sort of an interface between two things, namely the the active procedure, the topmost active procedure, and the procedure just before it that called it. So caller and callee, the terms that we use. So there's various information that can be stored in one or the other. It depends. You can credit it either way, depending on how you lay things out. So, for example, the caller, we can figure out what these are by just what programs do. So the callee, for example, has to know when it's going to return. It has to know where to return to. So the return address has to be stored someplace. You need the activation frame, the stack frame for the called procedure, or for the called procedure contains all this information. Well, so does, and everything that it needs to execute. Well, likewise, its caller has a stack frame that contains all the information that it needs to execute. So for that purpose, what you sometimes need to do, and we'll see why this is the case, what you sometimes need to do is to keep around information about where the caller is supposed to find its data. So that's something, we call that the dynamic link. The caller's, the information needed to establish the caller's, all the caller's information when you return to the caller. Then, if there are, I mentioned registers. So registers, you have to, if you want to use them, then there's a limited supply typically, and so you've got to do something with registers from that you want to use that your caller has also perhaps been using. So you can take the drastic step of saying, well, we will save everything in memory every time we call something. That way there's no problem. He can do what he wants with the registers, it doesn't matter. Or you can try to do a better job than that, and that results in a number of things called register calling conventions. Then you'll need, another piece of information you need is all the space for local variables. We will see actually that there are several different options here, but in general, a thing that you use activation records for are these local variables. And that includes, you'll need information to find variables that are not local to yourself. In a Python program, for example, you'll have functions nested inside each other. So, and at any given time, the innermost functions can access variables of the outermost function, of the enclosing functions. Well, how do they get that information? How do they get at those variables? Because it doesn't take too much thought to realize that the locations, the relative locations, are variable, and so there has to be some scheme that allows you to look at these outermost variables. So that information has to be stored. Then there will be intermediate results. You'll have complicated expressions whose results cannot all be put in registers. You'll need to store those temporarily, and so you need this activation record is a good place to put them. And then there's various stuff that's needed depending on the architecture. You'll have things like, for example, the flags the processor flags that indicate the floating point mode and stuff like that. Those will often get stored into the activation record. So, and then of course, just because, well, and then there's a question about who gets what, in other words. So the calling function could by convention get the return address and store the registers of the callee. That's possible. But there are all kinds of variations there. And also there is a choice that the implementer has to make about how much of this data gets put into registers. So there will be some things like the information necessary to get at the activation record that are best put in registers, because otherwise you'd be spending a lot of time reading things to and from memory every time you wanted to do something. So that takes a certain amount of organization. And it's also kind of useful if you imagine short procedures. It would be nice if you could keep some of the parameters in registers, if that's faster. Okay, so we have all of these problems that we have to deal with, and design decisions and so forth, but the basic idea is that there will be some body of data that contains information like this. And part of the problem is just organizing it to work properly. Okay, well, we will continue in this vein next time, and I'll see you then. Have a